He said, I just wonder what use it could be. But I'm so old, and you probably are, Walter, that I can remember when people actually answered the phone.
Yeah, yeah. Well, I remember when the first personal computers were made available, we had a large group of people together, and we tried to think what you could possibly do with a computer in your home. And finally, someone said, well, you can put recipes on it. Okay, we're going to get started because we have a big day. All right. I have to get to the beginning and full screen. So good afternoon and good evening and welcome everyone. Good morning in some cases. We're delighted to have everyone here for the seminar on this big volcanic eruption, which has captured the interest of emergency managers, scientists, and many people. As you all know, the event took place in Tonga, a country with many thousands of small islands located along the Kermadec-Tonga Trench. And this volcano that erupted is called a Surtsean volcano because it's similar to the island of Surtsey, which was formed in 1963 south of Iceland. And these volcanoes are quite special because they're so explosive. If you want to know more about or all the details on how these volcanoes work, the original paper is shown here, Journal of the Geological Society of London, 1983. And these eruptions are explosive because they're a mix of rapidly emerging magma together with a slurry of volcanoclastic breccia and water. And bang, it goes, as we saw. Now, the island that we're discussing formed in post-2010. It was already a subject of great interest and analysis by geoscientists. By 2014, this is the way it looked. You can see the circular shape in this year. 1.8 square kilometers of a volcanic tuff cone. And here it is in 2019 with a crystal clear image, very beautiful image. You can see the erosional features on the cone and also the origin of the name, Hunga Tonga in the northern segment, and Hunga Ha'apai to the west. So this is the volcano that we are looking at, and the one that erupted. Here we have an image of the volcanic cloud that inundated the whole area very quickly after the eruption. And the main island of Tonga is the lower triangle. Pangaea is up to the north. And to give you a scale, here's 150 kilometers from the caldera to the edge to the west side. So this is really a huge, tremendously huge cloud, as you know. We are only now beginning to learn about the damage. The telephone system came back up on January 19. Somebody has their microphone on and they have a dog in the background. Maybe you can just mute your microphone. Just everyone can mute. The size of the tsunami was 1 to 2 meters in Tonga, but interestingly, it was also quite about that size in the Circum-Pacific. We do have a report of 15-meter local tsunami and of numerous houses being destroyed. But as I said, the information is only slowly coming out because cell phone communication has been down. There's a huge pressure wave in the atmosphere, largest one recorded in the last 20 years. And as I mentioned, a Circum-Pacific tsunami. There are some important questions that are posed by this event. there was tsunami recorded on the tide gauges in the Caribbean and Atlantic Ocean. And there is absolutely no way to explain how a source in the Southwest Pacific using our usual understanding of tsunami propagation is going to explain a tsunami in the Caribbean and Atlantic Ocean. Another question that I get very frequently from people is how can warning centers estimate and give warnings, estimate wave heights for such volcanic sources? This is a really big challenge, and we will discuss that. Here is the outline of the 4 talks that are being given. Mine is almost done. You can read these yourself. And I'll end with a quotation. Nature never deceives us. It is we who deceive ourselves. And nature, once again, we are puzzled by this volcano and we'll try our best to understand it. With that, I will pass it over to speaker number 2, Jessica Reed. Jessica, you're all set to share.
Thanks, Walter. Hi, everyone. I'm Jessica, and I'm going to give a little bit of context from the tsunami record of tsunamis with volcanic sources. So this is a quick histogram that I made up, and the x-axis is time. This is all volcanic sources in the NOAA Global Historical Tsunami Database that have been recorded. So you can see a huge increase in number of observations starting around 1900, which is expected, but it's an interesting thing. It's a good thing to keep in mind. And so what we're looking at here is around 4 or 5 tsunamis every 20 years. So that's 1 tsunami every couple of years as frequency. Looking at that time frame from 1900, this is a map of all the tsunamis of all causes that were fatal, that caused at least 1 death. So these are the largest, the most socially relevant events. And you can see there actually aren't too many volcanic events. These are the red triangles. I just added this one most recently to show, but there really aren't that many. It's dominated by earthquake and landslide sources. And so these kinds of events that we just witnessed are very infrequent. This is a pie chart representation of what we just saw. And the numbers have changed a little bit because this is only to 2020, but in 120 years, volcanoes, these pink red sources, caused about 5.5% of all fatal tsunamis. But what's interesting to note is looking back at this map, some of those events were quite large, these big red triangles, and they're mostly concentrated in the central South Pacific region. So
lunging at a dog.
On the left, this bin shows all tsunamis that did not record a death. They didn't have any recorded fatalities. And you'll notice that there are a lot of them. And the red dots represent volcanic source tsunamis. And you can see there are some volcanoes that caused small tsunamis ranging from below 10 centimeters to a meter. But there are also quite a fair number of significant maximum water heights generated by volcanic sources. And on the right hand, these are all the tsunamis that caused fatalities. And you'll notice there are less of them, but there are a few volcanic sources that generated high water heights and a significant number of fatalities. This high one up here is the 2018 Anak Krakatoa event. It generated a maximum water height of 85 meters. Island that was really close to the volcano. And it also caused 437 deaths. So it was a very significant, large event. Aside from
said in a way that
only looking at tsunamis with fatalities can be flawed. So this distribution is all tsunamis that were caused by volcanic sources, regardless of how many deaths they caused. And it's scaled by, in this map, it's scaled by maximum water height. So we can see the size of the event. And this really large one is the Anak Krakatoa event that I was talking about earlier. And there are quite a few really, really extreme high water height situations, which is often a result of the volcano source being very close to coastlines and also having very large local tsunami generation. So this triangle would actually probably change over time, this new event, given the new information that's coming out. And finally, I wanted to remind myself that all volcanic sources are not the same. So we say it was a volcanic tsunami, but often it could be an explosion, or it could be flank collapse, a landslide of sorts. So the Anak Krakatoa event, for example, is colored green because while it was a volcanic eruption, ultimately a large part of the volcanic island fell, collapsed into the ocean, generating a local tsunami. And that is a really big factor in how the tsunami propagates and affects human populations. And that's all I have for context. Thanks.
Okay, thank you very much, Jessica. So we're ready to welcome Roland van Huene, Dave Scholl, who will be our next speaker. Dave, are you ready to share?
Okay, all right. I'll try what I can do. I'm going to share my screen. I got a PowerPoint, guys, and so I'm going to see what I can do here.
That's great. Should work fine.
All right, can you guys see
wow.
what's up
It
there?
looks beautiful.
Yeah, good.
Go ahead to the screen, full screen icon.
I will do that right now. All right, full screen. Come on. There we are.
Yeah.
All right, take it away, Dave.
Okay, let me, I guess you can see this better than I can. At any rate, so I just said, that is what the guys from the Tonga Geological Survey had gone out in a ship afterwards and got near the Hunga Islands. We're going to show more about this, but at any rate, this talk is on the regional tectonic setting. You know, is this island, where's it set up? What's going on? What's the regional thing for the Hunga Hapai and the Hunga Tonga arc of volcano? And anyway, so that's what was going on. And that was a pretty terrible day in Tonga Tapu, which is the island where these guys live. The Tonga Geological Service, by the way, a lot of it was set up by a friend of Roland's and mine by the name of David Tappan from the British Geological Survey. Anyway, let me go to the second slide here. Anyway, so I'm going to start with the settings, and I'm going to move westward from the Tonga Trench to the subduction system there, to the Tonga Ridge and the Tofoa Arc. You can call it the Tonga Arc if you want, but Tofoa is after the island of Tofoa, and it's under the volcanic arc systems. And if I've got it right, and I haven't checked this, but Tofoa was the island that Captain Bligh, when he was put in the water off the Bounty, he was said, row. They told him to row ashore, and he said, bullshit, I'm not going to do that. There are nothing but cannibals there. I talked with the Tongan guys about that, and they said, no, Tongan guys don't eat people until we learned that from the Fijian guys. These are the bad dudes over here. So they taught the Tongans how to eat British. And so I kept sailing. Anyway, so this is the setup here. And the gold colors, yellow gold is Fiji, Lao Basin. This is the volcanic center, the Hunga Hapai. Tonga Trench is here. but it's also connected tectonically to the Kermadec Trench down here, the Harv Trough, South Asia Basin, and so on. And the divide on all of this is where the Louisville Ridge, a seismic ridge, comes in and bangs into and collides with the Tongan Kermadec Trench here and divides them geographically and also structurally, as we'll see. So in order to set up the environment for what's going on here, we actually have to pay a little attention to what's going on here. So but let's look in a little bit closer here. And the eruption area here, here's the Hunga Hapai and the Hunga Tonga volcano location is right there. Well, Walter just showed a nice picture of the volcano before all this action took place. This is the Tonga Ridge, like so, and this is a residual chunk of Eocene, early Eocene volcanic debris with a lot of stuff on top. I'll show you a cross-section of that. This is the Tufoa volcanic arc. It's just off the backside of the ridge and sits on Lau Basin crust, which is Pleistocene in age. But I'm also going to show you information about the Valofau Spreading Center. This was picked up in '84. And Valofau, by the way, is a name that was given by the king of Tonga to this spreading center. When he heard about it, he said, well, let's just call it 84, because I heard about it in '84. And in Polynesian, it's Valofau. That's what 84 means. So we're going to talk about that because it's a very bright magma chamber that underlies the entire length of this spreading center. It's very close to hello, at any rate. So this is the index of that area. All right, so coming to look in here now, something I want to point out, there's a collision zone where the Louisville Ridge comes into the Tonga Trench here. Now, the underthrusting rate is very high because you've got back arc spreading in here, and you've also got trench rollback. And so it's 240 kilometers per million years. It's an extraordinary rate of underthrusting. The Louisville Ridge, where it collides, moves southward because of the geometry. It's orthogonal underthrusting, so each of these seamounts goes in like so, and that means the whole thing migrates southward. And it's setting up, as I'll talk about, the whole business of why is Lau Basin so triangular in its shape. So let's go take a look at a couple of things here. The seismic section, a multi-channel section of Tonga Tapu, very close to where the Hunga eruption area was. This is Lau Basin back in through here, and Tonga Ridge itself broke away from the Lau Colville Ridge here in the early Pliocene, something like that, and formed that basin. But when you look at this margin here, and you come down here, you can trace it all the way down to the trench. The trench has very little sediment in it. And you can trace geophysically, at any rate, the underthrusting into a bunch of gravens coming down through here. Now, ODP, back in 20 years ago, drilled here at 841. So we know something about what's going on here. And the discussion and the discovery here was, this was shallow water limestone sitting on some subaerial unconformities. It's that material right there, which is a 4.4 kilometers something right now beneath the seafloor, was at sea level. It's now down here, and you're very close to the trench. Coming down here to this seismic section, this is just past where the Louisville Ridge has collided and moved on. And we ran into this thing called, what the Tongans wanted to call it, the Motuku Geo. It's flat top. It's a very strange reflection. But the underthrusting seamounts here are geos, and they're flat top. That's, they've been eroded at sea level. So you can trace them geophysically as they go underneath the margin here. There's a lot of limestone and a lot of siliceous material on the top of this thing, and it's spread all around the seafloor there. And we can dredge all this late Cretaceous material, limestones and cherty material that got on the seafloor. So it moves down here, opens up the basin, and we're up here. This is where our eruption was.
This is a bad migration.
Okay, so taking a look here at 841. 841 drilled here. Middle Eocene platform limestones were discovered on subaerial unconformity, cut across 4-arc rhyolitic basement. So this is an old arc of Eocene age, what's left of it down here at a depth of about 4.5 kilometers, something like that. And here's the underthrusting seafloor. So that's where we are here. Iowa Island, which is right up here, straight above where we were. The same section is exposed on Iowa Island that you see out here, now under 4,000 meters of water. So if you look at this and you just play a little game with it, here's where the drilling took place. This is where the trench is. If you reconstruct this back up to sea level and put the trench where it belongs, then this is the remaining core of the Eocene part of the arc, and this in blue is what's missing. So you can decide what you want to do to get rid of that stuff, and if you get rid of it, where you're going to put it. But it very likely is going down the subduction zone and is getting down into the zone of melting beneath the Tofua Arc in one way or another. Okay, now let's take a look at the Tongan Ridge, which is out here. We're at the ridge now, away from the trench setting. And the whole thing starts, this is Dan Keurig, 1970 paper. It's a brilliant paper. It really set things up here. The Loyalty, Three Kings Ridge, part of the northern part of the New Zealand, the North Island part. At any rate, South Fiji Basin opens, and then we get the Lau Ridge, and that becomes a residual arc, and then the Lau Basin opens. So, hello, I didn't mean to do that. See if I can go back one. Yeah. And so the Tonga Ridge has migrated the eastern part of it all the way from here. And now it's running into the Louisville Ridge out through here. So this is sort of how Tonga got out here. I'll take a peek at that. So if we take a look at this now, we see where the Louisville Ridge is coming into is really not quite a hole in the margin here. This is the active Tofua Arc. A lot of active volcanoes all along through here. And the reason that the Louisville Ridge is interesting here is because it comes right through here, and all the volcanoes are extinguished in this belt. Down here is the Harv Trough and the Kermadec Arc. This is an active arc. Active, what I mean by that is that active volcanoes. This is a dead part of the arc where Louisville Ridge is under thrusting, going into the system. And on your left-hand side, it's sort of like right through here. This is just some good, well, I did the best I could to reconstruct where the Louisville Ridge would be underneath Lau Basin here. So here's the active arc. There's Boom Boom. There's our boy. This is the dead arc, and down here is the active arc. One of the dead arc systems is left here, and it's called Ata Island, A-T-A, Ata Island. Tracy Vallier, my buddy, visited that and collected some rocks from it. I will point out why that's significant. It's a dead arc. People have lived on it. People who get lost at sea end up on it. It's a really interesting place. Anyway, so this is the setup up here. Now we're going to go and take a look at Lau Ridge, and then we're going to go at Tofua Arc. So if we take a peek, did I go forward? No. Well, there we go. So here is a nice perspective drawing that Phil Barnes just produced. You can get his Twitter account and you can see this. Beautiful, I love it. But at any rate, we're looking at the top of the of the Tonga Ridge here. Sometimes we call this a platform because you can see all these flat, eroded areas with limestone on them, things of that sort. Here is the capital city of Nuku'alofa on Tonga Tapu. And this seismic section below, roughly the red line here, Iowa Island, that has the Eocene limestone exposed. It's also exposed all the way down this slope. So this is the pre-late Miocene Eocene basement to the Tongan system. All of this is debris that's piled up on top of that. You can see how it's tilted back and sunk. This is like the Nuku'alofa. It's a raised coral reef, or it's a Sangaman reef, whatever you want to call it. But this is the way it broke off from the Lau Ridge, and it appears that our Tofua Arc is coming through the Lau Basin Pleistocene basalt. That's the back arc, typical back arc spreading, and then the present Tofua Arc seems to be coming through that, best of our data. And then this is the residual piece of the arc, the Eocene, that goes all the way back to the Three Kings area. The Tofua Arc here is Hunga Tonga-Hunga up high, right there. And I'm going to show you something now with respect to These islands aren't here. These are submerged islands. Some of them come up. These are younger than these. So the younging of the Tofua Arc is to the west towards Lao Basin. So how do we know that? If you take a look, for example, at this line right here, a seismic line we collected in the 84, there's just a seamount we call GA, and over here is a seamount we call GB. We sailed right by it. The explosive of the Hunga Island is located right there. This is an old analog drawing, and so I put in the latitude and longitude of this island, and it's right there. And we apparently just went by it. We certainly didn't go over that thing. We went on to one side of it. But here's the key thing: when you look between GB and GA, here is did I get reverse these things? I hope not. No, I know. Down here, GA. What you can see is the GA's debris that comes off the volcano overlaps GB to the east. This is a better drawing. It was a little hard to see in there, but this debris overlaps an older GB, which is to the east. This is another area which is near the, oh, I see, I got a problem here with my, oh, well, can't worry about it. There, maybe you can see it now, but this is volcano Z, and this is volcano A, and you can see the same overlap. Z, which is to the west, is younger than A. And we saw this in 3 or 4 other places as well. So Tonga Arc, as it fires up at any rate, is moving slowly to the west. There's some interesting thoughts about why that should be, but the point is, I just wanted to point out the observation here about what's going on, arc, which erupted right here. Okay, let's see if I can get this. Yeah, okay, fine. Let me back up one if you guys don't mind here, make sure I know where I am here. Okay, we want to go now a little bit to the west, and here is Tonga Tapu. Here is where the volcano erupted. This is the Tofua Volcanic Arc. You can call it the Tonga Arc if you'd like. These are the platforms, the eroded tops of the arc. This is a spreading center. We picked that up in 84, and that's what the King of Tonga called it, the Valofa. It's half the full spreading rate is 65 kilometers per million years. If you'd like that, you can put that 65 millimeters per year. And so this is the Valofa spreading center. But as we went over this thing and noticed that it was there, what we picked up was very bright magma chambers beneath Valofa Ridge. And it looks like it's there, and this is another place where it's there. Wherever we crossed Valofa, which got named later, at any rate, we saw this very bright. A number of papers have been written about this, and apparently the main thing that's going on there is you're looking at a magma chamber with a lot of gas, a very low velocity structure, and acoustically you get a really strong feedback. The system we had was not that large, about 1,300 cubic inches, but a very well tuned on our ship, the Lee. So the interesting thing is this magma chamber is here, and the arc system is just kind of like right over here, about 30 kilometers away. What's coming out of that arc system, out of the Valofa Ridge, is an andesite. I remember getting up that night, talking with Tracy Vallier, who had the night watch, went on to the fantail, and there was a cup of coffee in my hand, and he was looking at me in the strangest way, because he just dredged the top of Valofa Spreading Center, and what was coming up was a very vesicular, like Swiss cheese, light gray andesite. And this is the chemistry on the andesite. Here, Ross, you see how very silicious rich it is. Okay, here's the average out here. And it's also wet. It's got 1.25, in percent water, which is very strange. Ata Island, this is part of the arc that died, and you still see the same sort of andesitic material there. So on the island, Ata Island, at any rate, on part of the Tofua Arc, and what you see offshore at Valofa, very, very similar sort of chemistry is coming up. So they seem to be linked in some way. So how are they linked? Well, here's a drawing, a model, I should say, I can't quite see things up here because I've got a zoom heading. I don't know how to get rid of it. Well, that's how I get rid of it. Okay, fine. So this is by Ian Turner and also Martin Sino, British guys. This is looking at the top of the reflections from the top of the magma chamber going along Vallefaugh Ridge. In other words, down the axis. So they trace this for about, 15 kilometers. And it's apparently very continuous. When you go across the spreading center, here's the ridge itself. You see it very bright there. Their model is something like this. There's their line 6. The magma chamber, the melt lens, they call it there, that's what we see very brightly acoustically. The magma chamber underneath it is the low velocity zone, and they have modeled it this way. And you see this melt lens all the way along here. I'm sure it's not totally continuous, but the Germans also came in here and a very similar thing was found. So this thing is just loaded with magma down there. But this is not the arc. We're 30 kilometers from the arc off here to our west. All right, let me get back up here. All right, so here's a sort of a model that Jenner has put together here in Journal of Geology, in which here is the Tonga subduction system. This is the responding, if you want to call Tonga Ridge or Tufloa Ridge, and here's Vallefaugh. That there is a mixing going on right in through here. They're so close together. So we get andesite here, sort of a water-rich andesite. We get the same thing under Vallefaugh Ridge. So Vallefaugh Ridge is a spreading center, but it knows that it's near and above a subducting slab, and it's getting juice from it. So our setting them for the Tonga Ridge for the eruption that we have is right in through here. And why it explodes so violently has to do with there's apparently a lot of volatiles being conditioned in this system. I'm not a petrologist or a magma chef, so I have to learn about why that would be. And I've been talking to some buddies about that, but I'm learning. Now let me go here to my last slide. I guess I got too far. Yeah, I just want to say we're not done. We've been talking up here, Vallefaugh Ridge, and this is the Kermadec system. This is the dead area where the Louisville Ridge comes through right in through here. And there are additional very large numbers of hydrothermal events and very large caldera systems, underwater caldera systems down in this part of the system. Here is what some of the names of some of these places. I love these things, Rumble 3 and Rumble, pretty neat. But anyway, there is much more to say about how this system works volcanically and what the spreading center is all about. But our setting, at any rate, up in through here, is in the part of the arc which is very volatile in terms of its ability to, explode like it did. And I look forward to hearing more about what happens here and why some of the tsunamis seem to have been so large and how it was generated. And we had to come here into the West Coast, into Santa Cruz, into the harbor. So it was a significant event. All right, that's me. I'm done.
Okay, let's allow very brief questions. Point of clarification: no long lectures to the speaker. If there is something that needs to be clarified, please speak up.
This is Steve Kirby. Hi, David. Thank you for your presentation. One of the interesting things is you're trying to figure out why this eruption was so big and explosive. And one of the things that is interesting is that there is a change in the tectonics, if you will, of back arc extension in the Lao Basin at about the latitude of this Hunga Tonga volcano, and to the north of that latitude, you have you have spreading, but also you have basin and range type extension, and you can see that by way of the scarps expressed in the seafloor. But south of that latitude, you have something closer to what we would call seafloor spreading. So I don't know what the significance of that transition is, but it seems to correlate in a latitude sense.
Yeah. Okay. Can you hear me still, Steve?
Yeah.
Okay. Yeah. There's a big transition. Can you still see my slide? Is it still up?
Yes.
Okay. Right in this area is the big transition. Very low spreading coming down here in Arv Trough, in the Arv Trough. Pretty rapid. But the basin, Lao Basin, is opening, see, sort of triangular, and it's opening southward. Valufa is the sort of the sphere point of the head of the sphere. As Louisville migrates to the south, it opens to the south, and you get spreading to the north of it. But it has not really much affected the Harv Trough to the south. So the extensional processes going on in Lao Basin have yet to visit to the south of Louisville Ridge, but it will get there.
Mm-hmm.
So, Dave,
yeah.
Based on what you've shown us, future eruptions are possible based on the fact that there is a clear magma chamber in the reflection imagery and young volcanoes.
Yeah, I would say so, because it's pretty gas charged. When we see acoustically these magma chambers so bright, I mean, they actually are jarring. When you first ran across them, we didn't quite understand what we were looking at. They are gas charged, very low velocity, gas charged sequences. So they're under the pressures of about 3 to 4 kilometers subsea floor, and I don't know all the details about it breaking through, but apparently you can stuff a lot of gas in those. It's just amazing to me how this sets up. By the way, there's very little sediment being involved in subduction here. When you get down closer to North Island, yes, you begin to get some, and that's where a lot of more work has gone on than up through here. So, but we're still getting it's a very gaseous system up here, and it's not clear to me why that is, except that subduction zones in general, can produce a lot of water and get it into the mantle. I could get some lessons on here, what's going on.
Right. Okay, that's fantastic. If you can stop sharing, that I don't know if you can see that, then we will move on to Emil Okal, for which we'll shift gears from the study of the volcanic back arc to observations of the eruption and the tsunami. So, Emil.
Yes, give me a minute. I'm trying to work out this thing, and of course it doesn't work. I'm never.
Take your time. Take your time. It just takes a little bit of patience.
I'm trying to get my file there, but it doesn't want to open anything.
All right, take your time. So for all those listeners, we did a test, and Emil was able to share his screen 20 minutes ago, 30 minutes. So be confident that we'll have it.
Wait a minute. Okay, here we go. And now I'm going to go full screen. Can you?
What we're looking at is you need to open your PDF. You need to open it before you share the screen. Maybe go out, open the PDF, and then do it again.
Well, it says it's sharing right now.
Yeah, we're looking at your desktop.
Yes. All right. So if I open the PDF, do you see it now? No.
Well.
Yes, I see what you mean. I need to open the PDF and then go to this thing here and say share.
Right.
And that should be open somewhere here. Okay. All right.
There it is.
Okay. And now I can go to full screen, right?
Right. Go to full screen.
If only I can find it, but full screen mode. Here we go. All right. I'm sorry, but computers don't like me. I try to reverse the favor, but it doesn't work.
I think that everyone who's listening feels an affinity to your problems.
Okay. So we are talking about the Tonga volcanic explosion. We've heard Walter's introduction, Jessica's in a sense explanation of its of how it fits in the tsunami record, and then Dave's very detailed explanation of a tectonic setting. What I'm going to try to do today is to tell you a little bit what a geophysicist like myself, primarily a seismologist, but also a tsunami scientist, what kind of data we can use and what kind of inroads we can make. So I remind you of the epicentral coordinates here. Well, the location was given by Dave, and the timing is about 0426 GMT, which was local time 1726 in Tonga. Now, there were actually two explosions. At 0414, there was a smaller one, which apparently didn't lead to any kind of wave activity. And then it was followed at 0426 by the catastrophic eruption. Now, the first reports, as was pointed out, the first reports from Tonga before about Monday this week indicated relatively minor waves, less than 2 meters, and mentioned no casualties. And they were probably limited not only to the island of Tonga-Tapu, but actually to the capital, Nuku'alofa. Now, the later reports, which have started to drift in, indicate a much, much greater damage. And we are now talking about 3 deaths in Tonga and 2 in Peru, by the way. There is a site in Switzerland, I think associated with the UN, which has put together a number of before and after satellite imagery pictures. And if you look at something like this, which is in Nomuka, which is this island here, you will see that there is a great deal of skyring.
I'm not seeing your picture.
Yeah,
advance your slide.
You need to move down to the next image.
Well, this is what I'm doing, but it's not working, obviously.
Try maybe the arrow up above, the down arrow.
Well, this is what I'm doing.
That's strange.
Well, as I said, computers don't like me, and I know it.
Why don't you go out and try coming in again and seeing if it works second time?
What? Stop sharing?
Stop sharing and try again. We only see your title slide. We didn't see you change the slide.
Okay, so now I share. Well.
Oh, there it is.
Oh, you see it? Now, what if I move? Do you see it?
Yeah, so it's working.
We're seeing it. Yeah.
No, it doesn't. The point is, it doesn't work in full screen or something. I don't know. But what you see here on the right is that there is a lot of scouring, for one thing. And then if you look at these houses, now granted, some of them may be under ash and so on, but clearly there are houses which are destroyed. And this was also reported by a gentleman whose sister, I think, runs a beach resort on Taga-Tapu, which is completely destroyed. And that kind of destruction requires waves which are greater than 2 meters. There is no way that you would have this kind of structural damage with waves less than 2 meters. On the other hand, those reports of up to 15 meters may be overestimated, because if the waves were up to 15 meters on Krakatapu, as you know, these houses such as this would be gone here. So we need to wait until there is a professional survey carried out by scientists, by professional scientists. Now, there was a classic tsunami. You get that picture now?
Yes.
Okay. And the classic tsunami, there is nothing much to tell about it. It propagates at the textbook velocity, square root of GH under the shallow water approximation, and it was observed throughout the Pacific with amplitudes which are anywhere. These are 0 to peak amplitude, anywhere from about 30 centimeters in Tahiti, expectedly, as always, more in the Marquesas, maybe a meter and a half in South America, with 2 casualties in Peru, apparently 2 ladies who were swimming in an estuary, which is not the thing to do when there is a tsunami, and similar amplitudes all around the Pacific. And I want to make a trivial remark here, that a classic tsunami, such as observed there, stops when it finds the shoreline. Okay? This is a trivial remark, but it's worth noticing. Now, the major question which was raised by none other than you, Walter, actually, about the regular tsunami, when we talked a few days ago, is why is it that the tsunami is so weak at the source as compared to faraway locations around the Pacific? And it's pretty much answered for the time being by the late reports from Tonga. The early reports were grossly underestimated. And as I said, a final quantitative statement to answer this question, we'll have to wait for a professional survey of the tsunami amplitudes in Tonga and around the Pacific. Now, if we look at maregram in Tahiti, for example, and I told you we had about 30 centimeters here, you see that the tsunami arrives at the predicted time, pretty much, but about 45 minutes earlier, there is a clear disturbance. And that disturbance, you can see that it's propagating at a group velocity which is about 313 meters per second, which is reasonably close to our familiar concept of 340 meters per second for the speed of sound in the atmosphere. Now, this is an air wave, and the reason why it's propagating a little slower than with the 340 is because it's actually channeled through various layers of the atmosphere. It's a very complex problem, and so the group velocity for this kind of air wave is a little below the velocity at the ambient conditions that we know of 340. So it's more like 313. And the amplitude is smaller. It's maybe 1/4 or so of the amplitude of the tsunami, and it is essentially, as I said, it's an air wave. Now, this kind of wave was studied before, and it was observed during the 1883 Krakatau explosion. By the way, Krakatau was until recently a nice place to visit. I'm here in September of 2016, sitting on a piece of real estate which no longer exists on the island of Anak Krakatau here. Now, locally, the 1883 triggered a big local tsunami which killed 35,000 people in Jakarta, and which was modeled classically by Satake and a student of his. However, the tsunami was also recorded, that tsunami was also recorded worldwide. They had a few maregraphs at the time, and here is a case in South Georgia, and here is a case in Colón, which is nowadays in Panama. Of course, in those days, it was in Colombia. And this was explained by these two fellows, Frank Press here, and David Harkrider, who happened to be my advisor at Caltech. And they wrote a couple of papers. The dates are wrong, I'm sorry. Harkrider started in 62, but the main paper on Krakatau is in 67. And they showed that the tsunami is actually this air wave, which is prolonged into the oceanic column and re-excites the ocean as it propagates. And in particular, the timing of the arrival here in places like South Georgia or perhaps Cologne here, the timing is about 313 meters per second. Now, I'm sorry, I scribbled this on sheets of paper yesterday night because I was really in a hurry to prepare all of this. The theory was given by Hackreiter in 1964. What happens is that you can consider, first of all, airwaves over a continent. And airwaves over a continent, they have many modes. Some of them are acoustic modes. Some of them are more gravity modes. But the acoustic modes propagate here at that velocity. This is the main acoustic mode. By contrast, you can consider an ocean. And if you consider an ocean, you just have a tsunami, a regular tsunami. And that regular tsunami propagates if the ocean is 5 kilometers in depth at about 210 meters per second and starts to be dispersed here outside of a shallow water approximation. This is all it's reasonably simple at this point. Now, again, this was all explained by David Hackreiter in 1964. You can find it, by the way, and this is where I took it from, in Ben Menachem and Singh, 1981, the handbook by Ben Menachem and Singh. And I don't know how these guys are not in jail because they lifted the text by Hackreiter verbatim without even an acknowledgement. Anyway, when the atmosphere, when you combine the two and you put the atmosphere underlain by the ocean, the two families of modes can be coupled to each other. What it means is that the boundary conditions that we have used, they are not really perfect. And those eigenfunctions, they penetrate the other medium ever so slightly. The coupling is sufficient to generate disturbances, for example, disturbances of the water level during the passage of the air wave, but it is not sufficient to affect the dispersion very much. So you see here that this mostly acoustic mode keeps, despite all this coupling which exists here, it keeps essentially the same velocity, and so does the mostly tsunami mode here. Now, what results is shown in that paper by Hackreiter in 1967. These are synthetics that he did for marigrams at the bottom and barograms at the top for Krakatau, 1883. And you have the fundamental acoustic mode here, which gives rise to this precursor, in a sense, to the tsunami. And then the overtone acoustic mode, which is an overtone of it, which we don't seem to be observing in our case here. And then you have a tsunami mode, the regular tsunami mode. So with this in mind, I should also mention, because that is phenomenal, that the grandfather, I'm sorry for the typo here, the grandfather of all airwaves is certainly the one which was generated by Tsar Bomba, which is also known as Ivan in Russia, which is the largest ever nuclear test conducted, 57 megatons here in Novaya Zemlya. And this is the kind of airwave which was recorded on a seismometer, pressuring seismometer in Tsukuba in Japan at about 6,000 kilometers. Now, no sea waves are known for this event, perhaps because we haven't looked. I don't know really, but I wouldn't be surprised if we did find some sea waves there. Now, there are a couple of exceptional and fascinating properties of these air sea waves. The first one is that it will not stop at a continental boundary. It will be converted into an air wave. This air sea wave, which has a part of its eigenfunction in the water, creating a tsunami, it finds a continent, and then it sort of converts back to the air wave system without the oceanic component, of course. And then it propagates over the continent. And when it finds another ocean basin, it converts back to the coupled air sea wave. And during all this thing, the speed of the wave is not really changed that much. And it remains about 313 meters per second. So the bottom line is that if you look strictly from a standpoint of an oceanographer, you would say, hey, the tsunami jumped en masse. And this is exactly what we see here, first of all, in the Caribbean. So in the Caribbean, I spent most of Saturday afternoon following these waves. And the first one I saw was in San Andres here, which is a Colombian island on the coast of Nicaragua, which somehow was forgotten when Panama seceded from Colombia. So it still belongs to Colombia nowadays. And you see on the marigramh at San Andres here, which I've reproduced at the bottom, you see that there is clearly a disturbance, not much, maybe 4 centimeters or so, but there is clearly a disturbance which arrives at about the time of the airwave at 313 here. And then you can follow this airwave all across the Caribbean. And there are a bunch of marigraphs, and one of them at Mona Island here, which is between Puerto Rico and the Dominican Republic here. And you see again that there is very clearly a signal, this time maybe about 15 centimeters or so, 0 to peak at Mona Island. Well, that's not the end. Let's go all the way, and I could show you, records in the Azores, in the Cape Verde, and so on. Let's go all the way to Greece. All right, many friends in Greece working on tsunamis, and they at Plymiri on Rhodos here we have a clear signal with a 0 to peak, which is again about 10 centimeters or so, and sure enough, what's the time here? What's the group time? It corresponds after 17,100 and something kilometers from Tonga, arriving here from the northeast. It corresponds to 313 centimeters per second. What is remarkable is that this wave has traveled approximately half of its path over the Pacific Ocean, and then half over Siberia and Russia, and it does find a little bit of water here in the Mediterranean, and that's enough to re-excite the surface of the ocean and to give rise to this record, which is again a marigram at Plymiri. So we see it essentially worldwide. Now, a second property which is also fascinating for those of you who are seismologists, you probably remember that seismic surface waves following large enough earthquakes, they can go around the world several times. And in particular, the simplest thing you can think of is that the surface wave goes to the antipodes and keeps going beyond the antipodes and approaches the station as a second passage along the major arc of the Great Circle as opposed to the minor arc, where, well, you know what? The air waves or air sea waves do exactly the same thing. They continue beyond the antipodes and they give rise to multiple passages like A2, A for acoustic, and A3 or air wave. Now, this is the same record I showed you at Mona Island in Puerto Rico, except now I'm looking at another essentially half a day more of record here. And you see that after this long time, I see the second arrival. And I've seen personally up to a fourth. Now, there is something which I don't understand, and this is one of the questions that we'll have to try to resolve in the future. We see that the second passage has a larger amplitude than the first one. Is this something to do with the fact that the source could be eminently anisotropic, that there would be at the source some kind of directivity? Is this a matter of propagation? I cannot understand. I cannot answer right now, but this is a point to be asked. Now, another property which is very interesting is that, like tsunamis, actually, air sea waves are very well recorded by long period seismometers, including horizontal instruments. And this simply illustrates the fact that, the Earth is not totally rigid. And so the eigen function of the wave penetrates the solid Earth and deforms its surface. And if you're lucky enough to have a seismometer there, you pick up the displacement. So here is Kodiak in Alaska. This is straight from Iris. This is a very broadband seismometer, which happens to be a horizontal here, and it's actually somewhat misaligned. The azimuth is 155 degrees, which is close to north-south, but still 25 degrees off. And you see, look, this is the time scale here is more than 10 hours. And you see the surface waves, okay, probably 1100 or something like this. And then probably multiple passages of the surface waves here. And lo and behold, after 7 hours, you see the air-sea wave, which is actually reasonably dispersed. And so you can use, because these airwaves are well recorded by long period seismometers, you can use all the techniques that we've developed to study seismic waves, such as, for example, spectrograms. So the spectrogram, essentially, you plot the amount of energy which is present as a function of time here and frequency. We go from about 10,000 seconds in period to 100 seconds in period here. And you see the first passage, the A1, the first passage of the airwave, the second passage of the airwave, and the third passage of the airwave here on this North South record at San Juan in Puerto Rico. There is some stuff here that I'm not exactly sure what it is, and this is part of the questions that will need to be answered later on. Now, another thing that you see is the very weak dispersion here. You see that the energy is shifted in time to the right, so the velocity is slightly smaller, but not by much. And this is absolutely typical of the dispersion of these airwaves as studied by, for example, by Kreider. So I'd like to end by saying what are the major outstanding theoretical questions here. One thing we don't, or at least I don't know, understand, or haven't really researched very much is what controls the ratio of the amplitude of the airwave that we could describe as some kind of pressure at the bottom of the atmosphere to the amplitude of the sea surface disturbance that we could call the quote-unquote tsunami, as recorded by a marograph. It will be obviously frequency dependent, but it should also depend on the water layer. And it should be a reasonably easy thing to investigate systematically. The second thing, there are things that I cannot explain at all. I showed you some records of horizontal records of airwaves, and it turns out that they are often, but not always, polarized close to transverse. And this is perpendicular to the Great Circle. You see Adak, Alaska here, essentially you have an east-west vibration, whereas the back azimuth is due south. So what you have is complete violation of the canons of elastic boundary conditions at solid fluid interface. And I have no explanation for this, and this is a point that we need to understand later. And finally, there are some arrivals which remain unexplained. You remember that question mark that I showed you on the San Juan seismogram? There is also, it was recently posted by Dr. Candela of Brazil here on the tsunami bulletin board. There is the sea surface disturbance here, which is recorded on a mariogram in Brazil. And you wouldn't believe it. It would appear to travel at about the tsunami speed, which is 200 meters per second, along the Great Circle through South. And they don't see the airwave really. Maybe that stuff here, but I'm not sure that it's not noise. So there are still many open questions. This is absolutely fascinating, we are just 1 week after the eruption, and we have made some progress understanding some of that, but we still some questions open. Something I forgot to tell you also. One of the things I do, and many of my friends do, is I always look for hydroacoustic signals, the so-called T waves, which propagate as acoustic waves in the water. And when you when you explode something in the water, you get a signal, a very strong signal. And this time around, the signal is minimal. My friends in Tahiti, they reported to me, and I observed also that the signals are incredibly minimal. And so that would suggest that the explosion did indeed take place in the atmosphere and not at the level of the water column. So I probably ran out of time, so I'll leave it there and I'll take your questions. Thank you very much.
Thank you, Emile. That was very informative and very well organized. Thank you for this comprehensive view. So it's open for any topic and any questions for any of the speakers. We can start with Emile, perhaps. That would be a good starting point.
Thank you, Emile. That was great. If I might ask him a couple of questions. This is Milton from Kona.
Hi.
Yeah, so of course I know you.
I know, it's great. We haven't talked since Sumatra, I think.
No, I saw you in Vienna at some point.
That's right. Yeah. So this is an incredible opportunity. Thank you very much for introducing the Earthwave to this community. Like, you're probably one of the few guys who got a chance to work with this signal. So we're recording this thing everywhere. And it's really good to know that there's like 2 to 3 generations of people who didn't know about these things, were never exposed to it. So this is a great chance for us to reintroduce this canon, this lore of knowledge to new people in there. And there's data everywhere. Even temperature sensors on satellite picked up like a ±3 degree difference from the wave radiating out. So this is a beautiful signature. And I just sent you an email just to say hi. So you know I am like fully invested in this for next year's. So what a great opportunity. Fortunately, there were not too many casualties, but presenting this is great to have your perspective and seeing the signals crossing things. Gerard was asking about this earlier this week. So you support this tsunami, basically Earthwave supported tsunami propagating across the world. That was my main question. Is that correct? You agree with it?
What? That the tsunami is carried by the airwave, of course.
Yeah, and it can jump continents.
Yeah. I mean, it's
awesome.
A main point. Yeah, Larry Brown, you have a question.
Yes, thank you.
I had a quick question. Could some of the complexity be due to reverberations of the coupled wave once it enters small bodies of water in some areas like in the Caribbean? I'm thinking of the Okashire Island case where you had basically the tsunami bounced around between 2 boundaries. And when they start to get into some of these more complex zones, could you get lateral bounces, lateral refractions, so to speak, or local reverberations from the bathymetry?
Well, it all depends on wavelength, first of all. Okay.
Yeah.
And the other thing is, I haven't thought greatly about it, but I would say that when the tsunami finds a big shoreline, okay, the airwave finds a big shoreline, it keeps going and it loses its tsunami component over Siberia, but it keeps going. I think it would be pretty robust, and it would take quite a significant structure, which would have to disrupt not only the sea and the shoreline, but also the whole structure of the atmosphere before it would affect the propagation very much.
Okay, good point. Thank you.
Thank you, Larry. Thorn Lay has a question.
For Emile, thank you for the summary. I agree with most of it, but there are 2 things that I don't agree with. One is that if you look at the dark wave recordings of the long period tsunami, unlike the example you showed in Tahiti, the arrivals move, the main arrivals, the long period arrival moves at about 310 meters per second. So it's moving with the land pulse in the atmosphere. And that's faster than tsunami moves. So what you have is a shock front driving the wave. So it's a driven initial tsunami. That's the biggest long period wave. And it does shed off energy just like a shock front will that then propagates at the normal tsunami. But so this is really well documented. If you look at the data in Japan, where they have the SNet plus seismic plus barometric pressure, and you can see that they're writing pretty much coincident in Japan. And I think that's true in most of the Pacific areas. So that's one point. And let me get my other one out, which is that if you look at the coupling between the land tilts in the atmosphere and the seismic stations, you have to be very careful, because I believe most of it on the horizontals is a tilt response. So the barometric pressure tilts the ground is very dramatic on the local islands. And you can't apply conventional seismic wave polarization interpretations to that data, because it's a tilt response to the loading from the passing of the airwave. It's much smaller on the vertical, of course. So those are the two things that I kind of had a quibble with here.
Okay, thank you very much. That's very very interesting, very helpful. I would like to mention yet that that raises the interesting question. You're telling me on the dots the main pulse is at 313, and but when you look at most of the marigrams in the at individual stations like the one I showed in Tahiti or in South America, the marigrams are at 210, and so.
Yeah, this is just a profile that was produced by a report in Japan showing the DART recording, and the slope of the line is the land speed. Okay,
now the second arrival would be the 210 over there, or?
Well, if it is a shock wave, it will be unstable and it will, shut off energy, especially if there are changes in bathymetry, I believe. So along each of these paths, this is global, so it's many different paths. But the first arrival, the biggest, longest tsunami, the one that's going to inundate the coastlines, is going at the land speed.
Okay, well, we'll have to follow up on this. Now, regarding your other comment, this is, of course, very interesting. My question, for which I have no answer, of course, is that in several occasions I've seen a distinct polarization perpendicular to or close to perpendicular to the back azimuth. And so it's not really a random thing, which because of the topography, the tilt that you mentioned could affect the response. I understand this, but the fact that it doesn't seem to be a random azimuth. It seems to be occasionally pretty close to being transverse. By the way, I didn't show it, but I looked at South Pole, okay? And South Pole should be a place where there isn't too much relief or anything, and it's transverse. So, I mean,
Okay, I think we have another question for you. Thank you, Thorne. Bob Stern, you had your hand raised.
Yeah, it's a general question. Do we have any samples of the material that was blasted out of the volcano? It'd be nice to know. Dave was asking me what the composition was. Oh, no, he was asking me what made it such a big blast. And I said, well, we need to know what the composition is of the magma as well as its volatile content. And for that, we need samples. Are there any?
Well, as you know, no outsider is welcome to land in Tonga at the present time because of COVID. They have a isolation policy, so it'll take some time before we get samples.
Is there an effort is the USGS have an effort to get some?
USGS doesn't presently. I'm in communication with people in Tonga, but what I've been told is, well, hold on. We're worried about getting water and a few other things done, as you know. But it's a good suggestion to get samples. I didn't ask for samples to be preserved. It's a good idea.
All they need to do is, they've been cleaning up their roofs and stuff. Just take a scoop of that stuff and stick it in a mason jar.
Yeah, that's right.
The coarser, the better.
Well, GNS probably is the best source for that kind of.
Eventually, GNS will get over there and do that. Gerard Fryer, you have your hand up. Nice to have you.
Recording in progress.
Thank you. Just a quick comment regarding Krakatau. There was the suggestion that that the explosion was actually a dollop of material going supersonic in the stratosphere, and that's why it coupled in with the air. The air channel, the sound velocity channel in the atmosphere so well. And here, without T phases, maybe something similar is going on here. Although I understand this volcanologist Cronin in New Zealand swears that this explosion was at a depth of 200 meters. So that's a very different situation. One other point is that the boom was heard in Alaska, but it definitely was not heard in Hawaii, and that's something that we need to explain. Thank you.
Well, the atmospheric situation is well known, and this is a qualitative statement, and it should be explained quantitatively. But it's well known for producing all kinds of shadow zones, and so there could be a particular focusing effect at a particular distance, which would favor Alaska over Hawaii.
One small commentary. Winter in Alaska with snow cover is very quiet. We have surf, we have a lot of ambient noise around us. And the signal, we might have a little bit in the audio range based on some of our records, but our ambient noises will be higher for tropical environments and surf conditions in Hawaii.
We have a question from Boyan. Go ahead.
Hi, this is Boyan Bang from the NTWC, National Tsunami Warning Center. I tried to start the video. Hi, I heard that the theory about the interaction, the air sea wave and the tsunami, and then that theory has an assumption that it happens in open ocean, so that the depth of the water column is 5 kilometers. That's how we get the 212 meters per second of the tsunami phase speed. So if it happens in the open ocean, why that dart wasn't triggered in the Caribbean Sea, for example? Or should it be detected on the dart record in Pacific Ocean too? Well, that's a quite intriguing questions. If the air sea wave and tsunami interaction is correct, I mean, in the open ocean.
I haven't looked at the darts in the Caribbean. I must say, there is so much data. I haven't had the opportunity to look at everything, and I haven't looked at the darts in the Caribbean. But the problem of the triggering of the darts is a very tricky one, because it uses an algorithm which is built on which is built on various kinds of thresholds and time averages and so on. So it may be that the dart did not quote unquote trigger, but still recorded on the coarser at the coarser sampling rate. I don't know. I cannot answer that question.
Something we have to investigate.
Yes, absolutely.
Yeah. Thank you.
So, Emil, what about tsunami warnings? Do these kind of sources present difficulties for estimating wave heights at different locations?
Well, that's not really a question for myself. I think the people at the warning centers would be in much would be much more competent to answer this. But I would say two things. First of all, and that may be more important, when a volcanic explosion is documented, then it might be worth putting into all the algorithms the velocity of the air wave to give some estimate of the arrival time. So, all the estimates that I've seen of the arrival times in the Pacific provided routinely by the warning centers were based on the square root of GH. And so it may be worth, if one is able to recognize a volcanic event, to also put in place some algorithm to compute earlier estimates of arrival. Now, as far as the amplitudes are concerned, I think this is pretty much everybody's guess at this point.
So, Stuart Weinstein, what did PTWC do in this particular case regarding forecasting the wave heights?
Well, there wasn't much we could do to forecast the wave heights. Our forecasting tools are set up for seismic sources. I know at NTWC they try to invert some of the DART signals, but we couldn't come up with a forecast that really made any sense. We weren't able to reproduce what even the DART signatures look like. So this was a pretty difficult event for us. Basically, once we had enough sea level measurements, we were looking at, of course, Nuku'alofa. 2 days prior to this major eruption, there was a smaller eruption that generated measurable waves at Nuku'alofa, and we have sort of an experimental tsunami detector that we've been working with, and we put Nuku'alofa in that detector. So our operations were alerted perhaps 15 to 20 minutes or so after the explosion due to the arrival of the tsunami at Nuku'alofa. Based on what we saw at Nuku'alofa and Pongo Pongo and French Polynesia, we started issuing threat messages for the Pacific Basin. But we weren't able to generate any forecast. And the challenge for both TWCs is, as you know, our products are basically seismically based or geared to seismic information. So we basically had to rewrite all of our products on the fly and try to do so in such a way that our dissemination software could still use them and put them where they needed to be. And that was a major challenge.
Yeah. Well, that's, and Eleanor, you had a comment in the chat box. Maybe you could just speak and tell people what you put in the chat box. I think she's trying to find her microphone.
Hi, everyone. I'm Eleanor Lutz-McMoore. I'm with the National Weather Service office here in American Samoa. For that evening, we were able to issue an advisory through PTWC, but it was a lot of the reports that were observed. I don't know if many of you remember the 2009 tsunami where we lost 34 lives. So a lot of the people were, when they saw the water receding, triggered a lot of the phone calls. And then when we had reports from our emergency manager of them receiving reports of neighboring Samoa, independent Samoa, of the inundation, that's when we hurriedly just issued the local tsunami warning for American Samoa. But we know it was a very difficult decision, not only just from PTWC because it's not a seismic event, but we had to react really quickly so we were able to evacuate all of the territory for that event.
What was the range of run-up heights in American Samoa from this event?
I believe Stu can give a little bit more, maybe a foot to 2 feet. Stu, is that?
Yeah, I don't know really what the maximum run up is. I can tell you that the maximum amplitude that we saw at Pongo Pongo was like 70 to 80 centimeters.
We never went back, we just got a bunch of videos from around the islands, especially from the areas that were highly inundated during the 2009 event, because we got a lot of the observations from the public for those areas, but we never went back out to do any assessments because then we had to change to a tropical depression, our focus for this week.
Okay, thank you very much. Some people still have their hand up who already asked their question. Probably that means they didn't put their hand down. But if there's another question, otherwise.
I had a follow-up, Walter, if I could.
Okay, go ahead. Go ahead, Thorne.
If you look at the seismic waves, and I could show it, the broadband recordings indicate that there's two primary bursts. So these are from vertical components filtered at 100 seconds and shorter, so it's high pass. And the origin time is the first one that Emil mentioned, but I guess maybe there's a 10 or 12 second later one. But what you see are these pulses, which are Rayleigh waves. And these are indicative of probably vertical blasts at the source. So if it's a reaction force, we can get the amplitude of force on the Earth that coupled into these as kind of solid wave LAM type phenomena. You excite the surface wave from the surface force. You can see it's very characteristic. There's stations at many azimuths and distance show these two pulses, and you can actually see it in teleseismic stacks in the P wave. The P wave is very small in these. It's probably these little arrivals that should be coming in about 100 seconds or one tick mark after the origin marker. So what will be interesting is to see if they can validate, and I think there is some satellite indication within the first few hundred seconds, they have an image and they can see two rings of expanding atmospheric shock. That these are primarily the input to the generation of the atmosphere.
I'm on the Zoom call, I can't talk to you right now.
So there's lots of seismic data, perhaps it will, and there's very little tangential. So it looks like an axisymmetric source. A vertical point force would probably do pretty well. Or possibly there could be some explosive component.
Why is the second pulse more complex than the first?
Well, I think it's probably two events, two bursts separated by about 40 seconds. And in the teleseismic stacks, you can see the first P wave, then something at 200 seconds and something around 250 seconds. And so there are discrete excitations within there. So you could deconvolve these by a vertical point force Green's function and try and get the source time function. That's sort of what we're trying to do. But you know, this is a insight into the explosive process. So those are within the first couple hundred seconds of the eruption. There's a lot of stuff later that is probably secondary events, but these two stand out as very characteristic. There's banding in the far field teleseismic stacks that suggests that there are multiple smaller eruptive bursts or impulses. And these are all before the arrival of the air, the LAM pulse in the air. That comes in right after the end of these seismograms. And then the ground tilts crazily and the displacements are unstable.
So how many seconds apart are they? I see the scale, 10 to the 2, so it's 100.
This is a 100-second tick mark, so these are separated by about 200 to 250 seconds. The first peak to these is 200, and then the second peak is 250.
So about 4 minutes,
Yeah.
Great.
So this is the substructure, and I think it'll be important to try and, if you were to try to warn about tsunamis from the seismic indications, you'd be seeing these signals before you get the air wave or the tsunami wave. You might be able to do something to at least recognize from the axisymmetry of it that it's not an earthquake. But I think it'd be hard for me to help Stu on saying exactly how strong the tsunami is going to be. You might be able to characterize the force and recognize it as an axisymmetric, likely explosive source or vertical point force, but quantifying it rapidly would be pretty tough.
Great. It's really good to look at data. It's really nice to see waveforms and get clarification like that.
I know the USGS. I haven't looked at it, but I know they computed a CMT for that. I mean, what was the percentage double couple they got for that? I was just wondering if we could look at that. If we're getting like 10% double couple, well, then we're dealing with an explosion or something. I don't know.
They did not post it.
Yeah, this is Paul Earl. We calculated one, but just basically to look at the relative amplitudes of the synthetics and the observed data. We didn't try to fit any type of mechanism on it. We just don't have that. We're not set up to model sources like this. And then for the magnitude, we used the surface wave magnitude and put a note on the event that this was not an accurate measure for the volcano, but just to give some rough estimate. But our moment tensor calculations and the surface waves were about the same magnitude at 6.
Okay, so it calculated at a magnitude 6.0 or around 6.
Around 6. I think we've got a 5.8 posted for it now.
Okay, all right.
But it is possible to do a moment tensor inversion, or not a moment tensor inversion, but a point force inversion. It's not routinely done at NEIC, but Hiro Kanamori set it up to do a W phase for a point force. So if you had the suspicion from initial analysis in the absence of love waves that it is a point force, that could be done by NEIC rapidly. But it's problematic because then you have sort of 2 stages. You have to rule it out as a conventional moment tensor and then do this other inversion, but they're done very fast.
Okay, thank you everyone for your questions, and to the speakers. We are going to keep the Zoom open. We're not going to close anything down, but I do know that a lot of people need to get on with other things in their busy Friday afternoon. In some cases, it's Friday evening if you're in Germany or France or Italy. But I would ask the speakers to hang out for a little bit more. We would like to grill Emil for a few more minutes. And thank you all for participating. And we'll reconvene with comments in a few seconds. But we give people a chance to sign out if they want to.
Bravo, Walter.
Thank
for
you.
Organizing this. Thank you.
Welcome, very welcome. Yeah, we're down to about 75. So Emil, you had 168 people listening, so it was quite a large turnout. This is a very good turnout for this meeting.
Well, it's not only me, it's the other speakers as well.
Of course, yes.
Thank you. It's glad to see a few faces whom I hadn't seen in a long time, notably from Hawaii over there, and Milton, Gerard, and so on.
Yeah.
Any questions?
Hey, Emil, I have one, just a simple one. With respect to the tsunami generation process, the mechanism at any rate, these are pretty large tsunamis, fairly shallow water where the eruption took place. what's generating these very large waves? Is it the shock wave? Is that what's doing it, pushing?
Well, yes, the point that you are making is that the water is reasonably shallow, and that traditionally a standard tsunami wave, which is generated on shallow water, falters through something called Green's law when it gets to deeper water. And that's quite well known, and this is why, for example, the Nias earthquake in 2005 didn't generate much of a tsunami. Now, in this particular case, if you have an air wave, fundamentally, I think if the explosion takes place in the atmosphere, you will not have any much of an influence, in my opinion, even though I'm not really an expert on that, but I would think that there is not going to be much of an influence from the depth of the water, which may be below that, on the amplitude of the air wave itself in the atmosphere. Now, the entire problem, and this is one of the questions that I want to look into, and which I mentioned at the end of my talk, one of the questions is, what is the ratio in the air wave coupled to the seawater? What is the ratio of the pressure of the wave to the amplitude at the surface of the water? And that is probably depth dependent, so depending on the depth of the water column. And I would surmise, I may be wrong, but I would surmise that it could be the other way around, that the deep water then probably creates a bigger wave, but I may be wrong. So I think that we have to separate really the tsunami where it's observed from where it's generated, because if it's generated through the air wave, the depth at the source may be quite irrelevant.
Okay, thank you. Amazing.
So why did Frank Press and David Hawkrider decide in 1964 to spend a lot of time looking at the Krakatoa record?
Well, Walter, because Frank Press and David Hawkrider, they were in the business of studying various things which happen up there in the atmosphere, and they were getting a lot of money for that. And they were intrigued by the fact that their database maybe was not natural. It was a little bit artificial, if I may say. And here is another case of something interesting.
Okay, so it was in part it was related to atmospheric testing. Okay, I don't know why I didn't think of that.
Not in part. It was totally related to atmospheric testing, I think. Okay.
I was trying to be diplomatic when I said in part.
They did have assistance, and that is Besemiani, 1956, because there was a air-to-water coupling following that explosion, which traveled across the Pacific. It was very small. But that is the other event. We don't just have Krakatoa, 1883. We have Besemiani, 56.
And that's very interesting because Besemiani is on land. It's not on the water.
That's right.
So it would go towards answering the previous question to some extent. There was clearly no water at all there, and yet there was an air-sea wave.
Okay, well, the discussion continues. Eric, what you got?
Sure. I was curious what's known about the polarization of the initial tsunami mode. Is it upwards or is it downwards? And does this shed light on the source process? I imagine the explosion would push radially outwards, imparting momentum, radially outwards. That would lead to an initial upward first motion in the tsunami. But then you've evacuated this whole region of solid earth, and then the water has to go back in and infill that. So is there is that outward or upward motion then followed by a downward motion from that backward flow of water into the cavity that was blown away?
Well, I would expect if there is an explosion at some height over the water, I would expect that it would push the water down. So that would...
Isn't the explosion sort of, I mean, I don't know why it's up in the atmosphere. It's down there in the,
well,
around the water surface, right?
The problem is if the explosion was in the water column, then we would have enormous T phases, and we don't. So I think the major part of the explosion may well be, and I'm stressing but may well be up in the atmosphere, not in the water column. This is a major, for example, it's a major difference with Sarigan. Sarigan was a volcano which erupted in the Marianas in 2010, and it created both an airwave, and a very small local tsunami, but it created huge T phases. So presumably at Sarigan, the explosion was either in the solid cone of the seamount or in the water above it. But in this case, the absence of T phases is something which is quite surprising.
But what's known about the tsunami mode? Was it upward first motion?
Well, from what the lady from American Samoa said, it seems that the first wave was a recess.
Was down, yeah.
And that would correspond to pressure of the explosion down and creating a cavity, which would move out to the nearby islands.
Okay, very interesting question. We have to keep looking for observations. Boyan.
Yeah, Emil talked about the ratio between the pressure and the response, the tsunami response. In a hydrostatic case, I mean, in oceanography point of view, is about 1,000th in a hydrostatic response. So 1 hectopascal change anomaly of pressure will respond to the 1 centimeters of the sea level change. So it is very minimal unless we have some amplification, either in open ocean or in a continental shelf.
The problem is that this is not a hydrostatic response. So it's a question of the very complex nature of the eigenfunction, which has both a pressure and a displacement component. And my hunch is, and I'm almost certain about this, that this is depending both on frequency and water depth.
I understand that. Yeah, I'm not talking about the hydrostatic case, but generally inverse barometric effect. This is the inverse barometric effect. Exactly. So pressure change, something caused the pressure change in the air, and that pressure change caused sea level change. That's what we call the inverse barometric effect. That 1 hectopascal is equivalent to the 1 centimeter of the sea level change. So, and then I just browsed the internet, and I found about maximum 7 hectopascal change in a pressure gauge. For example, the airport in the UK detected about 7 hectopascal of change, pressure anomaly due to the passing the wave, so air sea wave, whatever wave. But
so the millibar, right?
Yeah. Anyway, that corresponds to the 7 centimeters of the sea level change. And if it happened in an open ocean, then might have been detected by the dark sensor. That's my kind of first question based on that.
Well, the closest in measurement of barometric pressure from a seismic station at 760 kilometers was 5.7 hectopascal. So
okay.
Probably 5 centimeters to 6 centimeters of sea surface oscillation, because it goes up and then it flips sign and has about equal overshoot. So it pumped the water up and down a total of 10 seconds.
Yeah, they could have been detected by dark or.
Oh yeah, no, that's what we think happened. Yeah.
We have two more hands raised. Taro.
Yes, thank you. I'm Taro from Japan. I think we have sometimes observed meteor tsunamis on the western coast of Kyushu, Japan. The sonic wave velocity is around 300 meters per second, and the Proudman resonance occurs effectively at the airwave velocity is root GH. So in this case, root GH equals 300 meters per second. So H equals 10,000 meters.
Yeah, which means it's not Proudman resonance.
Yeah. So I think the tsunami generation was like meteor tsunamis over trenches. And so for example, around Japan, we have Mariana Trenches. And over the Mariana Trenches, the tsunami come later than the air pressure wave. I think so.
Well,
Thank you.
Well, there are several limitations to this model. I think one of them is that the meteor tsunami needs to be sustained over the entire propagation. Meteor tsunami in Lake Michigan, we have them, for example. It's something which keeps resonating as the weather front propagates. And so if you are thinking about Proudman resonance, you would need to have this equivalence between the motion of the weather front or the airwave, call it as you want, and the local square root of GH. You would need to have it consistent as the wave propagates. And unfortunately, you are not going to find an oceanic basin which is 10,000 meters deep. You can find a trench here and there, but once you cross the trench, this effect could not work. So I think it's quite a different phenomenon.
But I will study. But perhaps the distance from Tonga is very far, so perhaps it's the reason for generation of meteor tsunamis.
Because if you have the distance for Tonga is very far, as you say, but in order to have a generation with a meteor tsunami and be able to observe it in Japan, you would have to have this resonance occurring over the whole path. And it's not 10,000 meters. It's at most 5.5 thousand.
Okay.
Between Tonga and Japan.
Yeah, I will try to analyze it. Okay, thank you.
Okay, thank you.
Thank you for the presentation.
Maybe the final question from Liz.
I just want a question, because I've been looking at the data, and because we have barometric pressure gauges co-located with our water level gauges, what I've been trying to do is line up when we have the actual observable spike from the air pressure wave with our barogram observations. But if you look at someplace like Mayaguez, the Mayaguez station, for the first round, it's very well, the spike on barometric pressure and the tsunami observable are aligned. However, when you have the second one that you're talking about, the tsunami signal actually occurs more than an hour before we observe the air pressure wave at the station. However, when you observe the air pressure wave, you do see an amplification of the signal. But that timing is more coincident if you had a more classical tsunami that wrapped around into the Caribbean about 30 hours. So I guess my question is the possibility that we're seeing a combination of effects and sources on that second round that might lead to that larger amplified signal.
That's quite possible. So what you're saying is that I'm sorry, I didn't hear you very well because the microphone was chopping your speech. But So if I understand well, you think that perhaps also that a sort of regular tsunami would have come all around the Drake Passage and back into the Atlantic and up to Puerto Rico and arrived just about the time as the air wave was coming the other way around.
Yes, for the second one. And I actually have that on observable. The tsunami starts about an hour and a half or so before we see the air wave.
But something we can check by looking at other Caribbean stations, maybe.
Yeah, that's what I'm probably going to work on, is where we have co-located.
Yeah, Martinique, Grenada, and the coast of Brazil, we would perhaps see that effect. Yeah.
Yeah, and it does go all the way up into South Florida as well. I do have observations in Naples and Key West.
Okay, wow. Yeah.
Wow, very interesting. Okay, folks, we are coming up on 2 hours, and I do know the speakers are all hankering to go out and have a cigarette or a beer. So last.
Come on. I would like to say that, I would like to salute the memory of Professor Harkrider, and who was involved, as I mentioned. Yeah. He would not smoke cigarettes. He smoked cigars. Okay, full professors at Caltech smoke cigars.
David never seemed to drink beer. He also drank something a little bit more substantial, as I recall.
It's red.
Oh, I think he would drink anything.
Okay, on that note, thank you again to wonderful speakers, Jessica, Dave Scholl, and Emil Alcal, and to all the participants for all the great questions and lively discussion. We had a huge turnout, and people are still going to be interested in results that are coming in from all around the globe.
Yeah.
Okay. Thank you so much. Thank you so much, and thank you for all the questions, which were extremely interesting. Thank you.
Great.
Thank you, Walter.
Bye. Take care. Good seeing you all.
Thank you.
Congratulations, Walter. That was
it was a really good turnout. Lots of good discussion, and continues to be an interesting event.
Extraordinary, yes. I'm thrilled. It's just such fun to see people jumping on the data this way.
Yeah. Looking at the data is always great. Hey, Stephanie, thanks for inviting everyone. I think you may be muted, Steph.
Sorry. Yeah, a lot of people were there from NTHMP.
Yeah.
I think it's probably how we got Eleanor, which is awesome having her on. I noticed, Walter, at the peak, I noticed 171.
Oh, wow. That's really a lot. That reminds me, I have to turn off the recording.